Hi, my name is Nicola Ferrier. I'm in the Math and Computer Science division here, and I'm going to talk to you today about a project here at Argonne in edge computing, nominally in urban, but I'm going to talk about other environments too. And this is a collaboration. The leadership team is shown there, Pete Beckman, Charlie Catlett, and Rajesh, who couldn't be here today, but they are a large part of the work presented here is a collaborative effort between us and many others. So I'll tell a story today. I'll talk a little bit about how we started on this project, the phase one of the project, which is the Waggle Platform and the ArrayOfThings project, and then talk a little bit about where we are now and what we're working on and sort of what are some of the R&D topics. So it was summer of 2013, so just over 5 years ago, we were playing around with a project for environmental scientists, and they wanted to look at using a hyperspectral camera. And so we did a bunch of work out in the field, and you know, these hyperspectral cameras have anywhere between a few hundred and many, sometimes over thousands of bands of image data. And so each sample is about a 5 gigabyte cube image. And we wanted to sample about every 5 minutes, and we had students out in the farmer's field taking samples. And we realized that we basically needed to move a parallel computer out to the field to be able to analyze this amount of data. And so we started working on, how could we solve working with instruments of this level and this magnitude. So there are a lot of devices where there's much more data than bandwidth. And the hyperspectral imaging, LiDAR, radar, some of the cameras we've been looking at, light source data from like the advanced photon source. Often you need quick response. There's issues with privacy and security. And sometimes you want sensors that do smart things, like they sit there and they only transmit essential. You don't need all of that data from the hyperspectral camera. If anyone's looked at hyperspectral data, it's heavily correlated. You need to do a lot of processing. And the information in there is much smaller than the size of the data. And so, we wanted to be able to address this problem. So we started working on a platform called Waggle. And a version of the platform is the ArrayOfThings. So when I talk about a platform, people get confused because, and I'll try to give you some insight into these different variations on Waggle. But when you think about a platform, you have something, here I have a Ford F-550, and that can take various customizations. It can be a camper, it can be an ambulance, and actually at Virginia Tech, it's the periodic table, a food truck. And so we started working on this platform to address this, and the platform is called Waggle, and one customization of the platform that has gained a lot of recognition worldwide is the ArrayOfThings project. So inside there is the Waggle brain, and the Waggle's got 3 parts, and I won't really go into detail in any of these. I'll talk a lot about the edge computing, but there's a node controller that controls networking, security, and managing the system. There's power management and reliability. So these are devices that are going to go out and be placed in the field. And so we really have to work on the resiliency piece, because once they're mounted and out there, it might as well be a deep space probe. You can't have a grad student climb the pole and hit a reset button. So the thing has to work out in the field. And then I'll talk a little bit more in detail as we go on about the edge computing. So we put a computer out there because we wanted to be able to do all of these analysis of the data out there at the edge and not transmit things. So one customization of the Waggle platform is the ArrayOfThings project, and that includes a number of sensors, a sensor pod, and the brains mounted on a power pole. So what is the ArrayOfThings project? This was a large, major research infrastructure grant, a collaboration between University of Chicago, the City of Chicago, and Argonne National Lab to put a bunch of these devices out in the City of Chicago. So the ArrayOfThings has a number of air quality and environmental sensors built in to the device, along with our edge computing, which again I'll defer talking about that till later. And then of course, I'll go back to this pretty picture. When you are, this project we worked with the Art Institute, and so it also has some beautiful housing. You can actually go look at some of these devices. If you go out the door here and just around the corner, there's a bike rack and there's a bunch of devices mounted there. They are what we call the ugly boxes. They're the Waggle without all the beautiful housing. But you can actually go and look and feel, they're just around the corner outside the building. So this was, this project, the goal was to deploy hundreds of these nodes in the city of Chicago. And we have a bunch of other pilot cities, Detroit, Syracuse, Denver, Portland, Oregon. Many other cities are coming online, but a lot of people are also looking to deploy these units. So we now actually have them manufactured nearby. At first we were assembling them with students, and that wasn't quite the way to go. But a number of places all over the world are looking or planning installations of these devices. So this is a picture of the coverage in the city of Chicago. The red nodes are the nodes that went up in 2018. The blue nodes, some of them are up and some of them will be going up in 2019. And there's two circles drawn here. The small inner circle is a 1 kilometer radius around the node. The larger circle is the 2 kilometer radius around the node. And by the end of this year, 95% of the citizens of Chicago will be living within 2 kilometers of a node. So the nodes are providing rich data about where everybody lives in the city. And then, there's a number of different projects, but there's been a bunch of work there. These are EPA sites, and at the EPA sites, we have some nodes co-located with their very, very expensive sensors, and we've been working a lot on calibrating our inexpensive sensors with the expensive EPA sensors, trying to show that, lots of inexpensive sensors are giving us reasonably good data. So why do you want to put nodes everywhere around the city? Well, in the city of Chicago, and I think you can get similar data from many other cities, but this is a Chicago project, so it's very Chicago-centric. There's very different life experience depending where you live in the city of Chicago. So life expectancy varies dramatically in different regions of the city. Rates of asthma differ dramatically. Access to services, so this gives you some idea. There's these black regions. I live really close to this one, where to get into the city using public transit is over 90 minutes. This is using public transit, not vehicles. And then there are other areas where there's lots of access. There's a huge variation in access to grocery stores. So your experience in the city differs, and what we were trying to do was have a device that could actually give you that spatial and temporal resolution at a neighborhood scale. So let's just take a quick look at the asthma data here. So this is roughly the same, this region here is blown up here. If you look, there's these regions where there's very, very high rates of asthma. These are the EPA placements. These ones that are hard to see there, those are weather underground stations and purple air stations. So the regions where there is very high incidence of asthma, not only do we not have good sensor networks, we don't even have like weather stations there. So there are these huge areas where there's no data. There's high incidence of asthma and no data. And so we're going to address that by providing much more spatially rich information about air quality in all of these neighborhoods. Now, air quality matters, and these are some recent studies. This one's actually just this year, that they looked at schools. And there's this horrifying statistic in Chicago that something like 90% of all the daycares are within something like 100 meters of an interstate, which is a little distressing. When you look at these studies that look at the effect of whether you are upwind or downwind of the highway in a school. So they looked at students who moved from an elementary or middle school that feeds into a downwind high school or middle school in the same zip code, experienced decreases in test scores more behavioral incidents and more absences relative to those who move to an upwind school. So this is the kind of data you can start to collect when you have a very rich system. So the ArrayOfThings project supports many, many other projects with many objectives. You can go to the ArrayOfThings sites here in town and request nodes in your area, and every node that's placed, aside from our coverage question, is also, they're there to address questions. Lake effect, how does lake effect affect local air quality? There's one looking at air quality and noise in relationship to people's health. There's traffic patterns, a number of different things, and we actually have a huge educational component where a local high school is using these in their curriculum to learn about computing and how to build sensors and devices to answer questions. So there's a lot of projects, and I realize you can't read that, but the idea is that this supports a lot of projects. So that's kind of that project's been, the nodes are being deployed and it's ongoing, but one of the things that we noticed was, you can deploy the Waggle platform. It's very easy to attach any other sensors that you want. We have all sorts of good description on our website. You can integrate other sensors and devices. But what's really interesting is there's a lot of measurements that we're interested in and questions we want to ask that can't be electronically sensed. And so you want to know about things that happen that there isn't a sensor out there that you can buy and have a Linux driver for that we can hook up to our Waggle platform. You want to ask questions. A good example is near misses are rarely reported. There's no data. So you don't know if there's a near miss because there's no data. You don't know we have a lot of at-grade rail crossings here in Chicago. And after, this is real footage from Auckland. So after the rail bars go down, they have no data on how often is an emergency vehicle impeded. What's the average length of time an emergency vehicle is impeded? And so these are the kinds of measurements that we want to make using things like cameras and machine learning and having devices out at the edge that can measure and answer these questions that are not, that require software and algorithms, not necessarily a sensor. So all of the first round of nodes didn't have cameras, and we've been putting cameras in, quite a few of them, particularly if the questions asked for those nodes are things like traffic patterns and whatnot. So most of the new generation nodes have two cameras. One is looking up, one is looking down, and the images on these were being, in the first round, were being processed by our edge computer. As we were doing all of this work, there's been, as everyone in this room probably knows, a huge explosion in machine learning and tools, and our computer supports all the software stack of your common libraries, but we also noticed it wasn't beefy enough. We don't have the compute power to do all the things we want to do. However, there's been this explosion of machine learning inference accelerators or machine learning devices, and our new version of Waggle that we've been testing out since this summer includes a number of these devices like the Google TPU, the Intel Neural Compute Stick, NVIDIA's Nano. We've been testing all of these and benchmarking them in order to make our next generation platform able to handle these large data streams from multiple cameras. So what we can do now is we can define software-defined sensors where our node, as I said, it's open source and easily extendable. We can deploy different software to answer different questions with these software-defined sensors that are based on the algorithms used to analyze our image data or our audio data. I won't talk about audio today, but there are also audio things. So right now, we can do things like on the Chicago Botanic Garden's roof deck. They're looking at how different plant species handle different levels of moisture, and we have platforms up there looking at plant species. We can look at pedestrian flow, traffic flow, wildlife in the city. This is with the Lincoln Park Zoo, clouds and cloud coverage. And so, you know, the city of Chicago, and I think most other cities, are interested in looking at movement of people and traffic. And so we've been tracking, these are actual real footage from our AOT nodes on Lakeshore Drive, and we have a computer vision machine learning system running here that's identifying things. And you can't read it, but you know, it's got people and car. Most of them are correct. This is a bus, it knows it's a bus, although it thinks the bendy part of a bus is a suitcase. So we still have a little work to do. It's really glad that those print small. We have a project with the Chicago Bears. They are interested in detecting drones flying above the stadium, not for safety, as most of us would think, for illegal filming. So we had an Air Force fellow here that worked with us on developing the algorithms for the upward-looking camera that can successfully detect drones versus commercial aircraft versus birds. So these are the sorts of things you can do with sort of existing machine learning, but there's all these other things that are of interest. Chicago suffers from horrible flooding in housing. This is reports of basements flooded in, I can't remember what year that was, I think 2014. And we have nodes being deployed trying to look at urban flooding. Now when we go to do urban flooding, we have to change the algorithms we're using. And one of the things that we've been trying to do is have prediction based on local weather and other information in our models running help drive what models we run out at the edge and where we're looking for flooding. Similarly, this is in collaboration with CSIRO in Australia, and Nikhil comes and spends large amounts of time here at Argonne. Again, they are looking at sensors out there looking for fire. There's also some flooding, but fire. And they're using analysis from various simulations to figure out impact, to figure out response. We also have a project here at Argonne that will be starting very soon with the folks at San Diego. The project there is called HP-REN. It's a huge NSF-funded project. They're looking for smoke and wildfires. And again, it would, instead of just computing at the edge, we'd also like to be able to have this our HPC models help feed into what are we doing at the edge, how are we processing, and what's the most valuable information. So that takes me to sort of the futuristic, or where are we headed with this work, is when you're at the edge, edge computing, there's sort of a model that people are pretty comfortable with right now. You collect a bunch of data, you deploy an inference engine at the edge that analyzes your data. And this is fine, but it's somewhat static. And we would like to figure out, and we are working towards having a more continuous feedback loop. So as you're collecting data, you also, you use your HPC system to figure out your models, your optimal models to use. But we'd also want to tie in with all of the tools that have been developed over the last, many years with simulation, forecasting, and modeling, especially for things like flood, fire, and other things, to be able to help address what's going on out at the edge and change the algorithms we're using. And so we've partnered recently with ARM, which is the Atmospheric Radiation and Measurement Facility. It's an Argonne facility that actually is in the southern Great Plains in Oklahoma, and they have a tower there, and we're looking at how do we take what we're doing here and apply it to LiDAR data. We're also working with some folks at the Advanced Photon Source, which is our big light source over here that also generates lots of data. And the idea now is that rather than having this static system, we want to have this interactive system. Now this is going to take some changes because you'll notice things. So I'll give the LiDAR example here. So LiDAR in the past, people are out there, they collect data they sample it at a fixed frequency. But that's a lot of data, and you often don't need all that data, and you don't really care about the frequency. There are periods of time where you want more spatial and temporal resolution, and other periods where you don't. And we have an experimental LiDAR that you can actually direct and you want to interpret your readings based on things like cloud cover and context. So this is sort of a great example where we want to collect some raw data, analyze it. So here's one of the caveats at using HPC. We would like a real-time trigger to trigger particular calculations based on what we're sensing out at the edge. And this is going to take a change of policy because I don't know about you, but I can't get a job when I want it immediately. I can't steal all the resources I need to do a calculation. But as you're collecting data, there are times where you need to change the model. You might want to change what model you're running, change parameters based on what you're sensing, and then you want to go back and steer or direct. So the LiDAR we're looking at, you can actually direct its, change its position to collect different data, and you can change the sampling frequency and other things. So this is sort of the feedback loop that we would like to see envisioned. We haven't figured out how we're going to do that piece yet. And you know, there's a lot of pieces that go on here, but as you're collecting the data, you want to be able to use your other things like your cameras. So we want to detect cloud cover, percent cloud cover, what's going on, and use that to interpret our data and change the algorithms we're using, possibly switch what processing you're doing. Maybe you've got enough data that you want to start looking for fire or floods. And so this is the piece that we're currently working on, and you know, fingers crossed the DOE will hopefully soon be funding, because we put in a proposal to do this in May. And so this is kind of where we're headed with computing at the edge. So there's some pieces that are, you know, we have a lot of experience, but how we tie this in with the large scale computing and simulation, we're still working out those pieces. There's a lot of things that need to be resolved. We can solve almost any of these problems on an individual problem basis. We can figure out how to do something, but we're computer scientists, so we're thinking about, well, how do we do this more generically? So when we built the Waggle platform, we didn't want to build just the ArrayOfThings platform. We wanted to build an edge computing platform that allowed you to integrate multiple sensors and devices. In the same way here, we want to think about how do we do this continually improving edge to HPC system. You know, how do we do steering to more domain of interest? How do we have an event-triggered deployment at the edge and at the HPC system? What does that mean for our runtime and software system? Because what I would like is to be able to say, I need to solve this problem, and you know, maybe it happens at the edge, maybe it's too computationally intensive, it needs to be sent to the cloud or somewhere else. So there's a lot of questions that need to be answered in terms of, you know, what does the programming model and framework look like for what we're calling the continuum computing, from edge to fog to cloud to HPC. This should be a streamlined process, and right now it's not. You know, we can develop individual solutions to individual process, but there isn't really a programming model that knows how to trigger the different devices and the different compute resources as you need them. And then for AI at the edge, we need some sort of resource management and inference policy. So the policy with Waggle was that this is a shared device, and right now you can get at all of the data. It's all online, anyone can access it. There's a bunch of software tools and APIs. For the edge computer, we haven't figured out how we do that yet in a secure and safe way. So we can, you can get a Waggle device, you can plug it, set up a new sensor and integrate it. We have not figured out for the software-defined sensor how we safely allow people to get it at that level of control of the device. And security is important. We have, knock on wood, not yet had any incidents, and we've really set it up so you can't actually get at these devices except maybe with a baseball bat. So, and actually they're positioned high enough so if 2 6'2" guys standing on each other's shoulder with a baseball bat, they cannot reach them. So You laugh, but that is how we picked the height. It was really security for the device. So we have a lot of research questions that we're addressing, and we feel that it's a very exciting time. There's a lot of research to be done, but there's a huge amount of opportunities. I haven't talked a lot about the urban science, where it's going, but there's a lot of social questions. When we get this AI at the edge running, and we can do all sorts of analysis of not just pedestrian, but pedestrian motion, pedestrian interaction, there's a lot of social scientists at University of Chicago that want to answer questions like, how are people using the parks? How many people are using them, and in what manner are they using them? Because there's studies showing correlations between park visits and reduction in crime in neighborhoods. So this is a really interesting question. They have very crude numbers. Like we did with air quality, they'd like to get fine-grained answers to people, how many people are in the park, when are they in the park, what are they doing in the park? So what are they doing in the park is a very different question than just counting people going in and out. They would like to look at interactions. There's actually a very interesting app that has been developed at Chicago that, like a Google walking app, if you ask Google Maps to give you a walking path from A to B, it's not usually very nice. I mean, it's not necessarily nice. And so his app, this is Mark Berman, it tells you where you can walk, where it might be more tree-lined, or might be, you'll experience more nature. So he has this app. The question is, do people use it? Is it effective? We could start to answer some of those questions. So that's where some of those, once we have the AI facilities running at the edge, we can do all sorts of exciting research. So I'll close with a quote from Kurt Vonnegut, actually a quote from Kurt Vonnegut that you can put up on a public screen, which is, I want to stand as close to the edge as I can without going over. Out on the edge, you can see all kinds of things you can't see from the center. Big undreamed of things. The people on the edge see them first. So, okay, this is about people, but we really think that when we get an edge device out there that can do all these clever things, there's all sorts of opportunities that will open up. With that, I'll leave with our websites that you can have a look at all of the gory details and acknowledge, again, this is funded by NSF and the City of Chicago and the DOE, and it's a collaboration between a number of different institutions. With that, I would take questions.
I know it's not part of the plan, but has any thought been given to, integrating this eventually with things like traffic management and so?
Oh no, it's been part of the discussion.
Okay.
And so we aren't there yet in the, we're just now looking at how to do device control, but I know in Detroit they're very interested in looking at how to change traffic management. We're using it as a collection device now for policy. So we have some going up at O'Hare for the expansion project, and we do have some going up at railway crossings but we haven't actively controlled devices yet. But it is part of the thought process.
Thanks, this is very exciting. I don't have a real question. I just want to kind of make sure you're connected with some people. As you were talking, it occurred to me that this is something that Ruby Mendenhall would be quite interested in from somewhere in Chicago. And also the Brantinghams at Simon Fraser in Vancouver have been doing a lot of work in computational criminology about sort of geographic information systems and relating them to stuff like that. So it's sort of a shout out for you to them.
Okay.
I'm hoping that, I can connect to you if you'd like, so.
In the news in just the last month or so has been quite a bit about facial recognition activities. Does this have anything to do with the methodology or activities that you're doing?
We have not done anything with facial recognition. And actually, we had a lot of community meetings with the people in the city of Chicago, and we have really strict data use agreements. Mostly, we're not all that interested in the facial recognition problem, but we're interested in motion and stuff, but we also can't transmit images from the AOT nodes. Now, we have some that are Waggle, and we have some agreement to collect enough data to do some analysis of how our algorithms are working, but one of the agreements was very much in protecting privacy. So we're not interested in who people are. I know that could be done. And of course, from our positioning, 22 feet up, it'd probably be pretty tough to do facial recognition. But I'll tell you that there's pretty good work done on recognizing people through their mannerisms and gait. And so if we really wanted to go there, I suppose it's there. But we're really, that hasn't been. And it's something we're really concerned about because we want the people to feel comfortable and welcoming of these devices, and we don't want them to feel like we're checking out who's where. I think the easier one is if people use software-defined radios and they can detect your phone and figure out where you are at all times. Those would be the people I would worry about, but we're not doing any facial recognition. We could, you could, but we haven't done that.
Last questions? One behind you, Lloyd.
This comes from, we've got systems, that if a hard drive dies, if a memory dies, if something dies, we can automatically call you and say, actually we can automatically call Supermicro and say, send a replacement, okay? So what I'm thinking is, someone gets hit by that train, right, God forbid, right? But if someone gets hit by that train, call an ambulance. That would be awesome if we could do that, right? Not just track them that they almost got hit, but if someone actually does, automatically call an ambulance to get somebody there as fast as possible, right? In the same sort of way as when we have a problem in one of our computers, we instantly call service to go take care of it.
So we've thought of that, and one of the things there's been a lot of work on back to the traffic and could you do controls. You've got someone who's disabled or elderly or in a wheelchair or something crossing the road. You might need to delay a light. So we've had these conversations. There's a lot of hurdles to get that in place, but yes, those are the sorts of things that this is where we think this is going to have a lot of value.